Chapter 6, differential equations. Please take a moment and copy these into your notebook. A differential equation is an equation that involves x, y, and the derivative. So we've been studying differential equations. This is represented by the derivative, so that's not new to us. In this chapter, so over the next 3 days, we'll look at analytical and graphical solutions to differential equations. We'll look at separable differential equations and growth and decay models. So it is a brief unit. Analytical solutions using calculus techniques. So given the differential equation, okay, and this will not be the new part for you, how do we solve a differential equation? That's me asking you, here's the derivative, you find for me the function, f of x. So we've looked at, we multiply by dx, bring that over to the right hand side, then all the x's are the same, and then we integrate both sides of the equation. So now technically this should be a capital F to represent the antiderivative. Remember that this is referred to as the general solution, okay, because it has the plus c in there. And if we are given some type of initial condition, then we substitute into the function and solve for c. If we can determine what c is, then this is referred to as the particular solution. We studied this at the beginning of chapter 4. We looked at it again last chapter. It was on both your quiz and your test in chapter 5. Find a function for y given this differential equation. So we start by bringing the x's to the right hand side, integrate both sides of the function. Integral of secant squared tan x, integral of 2x is x squared, integral of 5 is 5x, and then plus c. So this together is the general solution, and y because no initial condition. And therefore we can't find the plus c. Remember, we need the plus c because the derivative of y would give us secant squared x plus 2x plus 5. So regardless of what that constant would be, the derivative of a constant is always 0. So for the general solution, we need to include that c. Find the particular solution to the differential equation whose graph passes through the point 1, 0. Bring the dx to the right hand side, integrate both sides, integral of e to the x is e to the x. So the integral of e to the x is e to the x, the integral of 6x squared is 2x cubed plus c. Now that we're given some initial condition, we plug those values in for x and y to solve for c. So 2 minus e equals c. I'm putting it all together. This is our final answer. And again, that's the particular solution, which the directions are very specific to ask for. And if we just stopped here, that would be our general solution. But both of those functions, the general and the particular, have the same derivative, which is e to the x minus 6x squared. Okay, now the second thing we study, which is brand new, are the graphical solutions to differential equations. And in order to solve a differential equation graphically, we use what's called slope fields. So I know that this looks brand new, but you've seen this in your homework. We just never actually looked at what the graph is. All right, so a couple notes about slope fields. Each tiny segment that you see on both of these graphs, each segment represents the slope of the function at particular points. Okay, so the slope field represents exactly that. So this represents the slope at every single point on this graph of f. Okay, we don't know what the function is, we don't have an equation for it, but we know the behavior of the function. Now think way back when, if we're looking at slopes, if we have a positive slope, what does that tell us about the function? We know that our function is increasing. If we have a negative slope, we know that our function is decreasing. Okay, and slope and derivative are, we can use them hand in hand. Now what else did we learn when we interpreted graphs? If our slope is increasing, that tells us our function is concave up. And if our slope or our derivative is decreasing, that tells us our function is concave down. So now the goal, we're going to use these slope fields and sketch a graph, and that graph will represent the function. So using the slopes, we can determine particular information about the graph of the function. So again, the solution is the graph of y, not necessarily the equation. So the analytical solution is using calculus techniques, integrating and finding a function. Sometimes that's not possible. So we can attempt to sketch a graph of the function and not actually know what that function's equation is. So again, dy dx gives the slope at any point on the function, on the plane. Given an initial condition, you may or may not have that information, and we'll talk about that tomorrow in class. If you are given an initial condition, solutions must pass through that point and be tangent to each of the little slope segments. Now we will practice this in class. Use the slope field to sketch a solution of the differential equation. Okay, now notice there's no initial condition here, so there's multiple answers that could be true. Alright, so look at what's happening here. If you can see on the x-axis, there's little horizontal lines. And now just look at this, okay? So don't sketch these into your notebooks.
All special ed teachers, please report to child study team. All special ed teachers, please report to child study team. Good day.
Okay, so look at what's happening. Slope on the x-axis is 0. Above the x-axis, all those slopes are positive. So it tells me that my function is going to be increasing. Okay, I can also see from the slope, let me put this up here. Up here, dy dx is positive, therefore my function is increasing. And secondly, dy dx is increasing, and therefore my function is concave up. Now, from the notes here, the solutions must be tangent to the little slope segments. So slope of 0, that's one solution. I don't know any particular condition. Now let me look down here. Below the x-axis, my slopes are all negative, therefore my function is going to decrease. And my slopes are decreasing, so my function is going to be concave down. All right, my function starts out, and then I'm tangent to the slope segments. So that could be a solution to that slope field. Now again, I don't have a particular condition, so these are just sketches. And multiple sketches are appropriate if you're not given any information about the function. All right, so now let's look at this slope field. Okay, negative slopes here, so my function is going to decrease. Slope of 0, so I'm going to have a turning point. And then look at, this would be, my slope is approaching, my function would be approaching infinity here. So function decreasing, decreasing, turning point, and then it's going to hug that line there. Now on the right hand side of that, notice that my slopes on this side are negative, so my function is going to decrease. And these are only sketches, and what we'll talk about when you prepare for the AP test, it's truly that. As long as the behavior is correct, as far as function being increasing, decreasing, concave up or concave down, you're in good shape. Okay, so I will want you to put this in your notebooks, please. Construct a slope field for the given differential equation. Okay, so notice, and you'll be asked to do this more than likely on the AP test. Here we have a coordinate plane, and you have 12 points given here. To construct a slope field, what that is asking is, here's a function, now you draw the little line segments. So the easiest way to do this, make an XY chart. So I'll start where x is equal to -1. Okay, so here's the point, -1, -2, -1, -1, -1, 0, and then -1, -1. Now how do I find dy dx? Well, we're given the differential equation. So we replace our x's and y's with the appropriate values depending on the point where we are. -2 plus 2 gives me a slope of 0. -2 plus 1 gives me a slope of -1. -2 plus 0. And then -2 minus 1 would give me a slope of -3. So now at these exact points, we draw tiny little segments with the given slope. So -1, 2, the slope of the function at that point is 0. So horizontal line. At the point -1, 1, the slope of the line is -1. So I draw a segment with a slope of -1. At -1, 0, the slope is -2. At -1, -1, the slope is -3. So our slopes, notice what your dy dx is doing here, it's getting smaller. Okay, so now we can look at all the values where x is equal to 0. 0, 2, 0, 1, 0, 0, and then 0, -1. Plugging that back into the differential equation, 0 plus 2 gives me 2, 1, 0, and -1. So now I have a positive slope at these points. So +2, +1. At 0, 0, I have a slope of 0. And then at 0, -1, now my slope is negative again. So for homework, in class tomorrow, complete the slope field for the remaining points. See you in class.